Okay, you've made it to lesson 9.5, and we're going to now integrate things that involve inverse trig functions. So from last lesson, we learned that the derivative of arcsine of u, of course, is just 1 over the square root of 1 minus u squared with an extra u prime. And this arctangent 1 equals to this. We don't usually use cosine, arc cosine, because it's just a negative of the arcsine derivative. So, hey, why bother with two things when we just use one? Now, going backwards, however, if I ask you to integrate something like this, where the denominator has 1 minus u squared and the numerator has u prime, then you get back arcsine. Similarly, the integral of 1 over 1 plus u squared with an u prime on top then becomes arctangent. So we can extend these integration rules, and if we do that, we get more what I call general integration rules for these inverse trig functions. And this time, instead of having a 1, I've changed it to some other square, so a squared. And if you do that, it changes the function part here. Instead of having u, it's now u over a. And similarly for the tangent 1, instead of having 1 plus u squared, now it's a, and I've got this 1 over a factor and a u over a in the end. And you're like, where do these things come from? Well, I'll show you an example in a second, but bottom line, if you don't want to go through this process of, and I'll give you a hint right now, it'll be lots of U-Substitution, then you can just use these formulas. Okay, so either memorize or understand where they come from. Okay, and as I said before, since arcsine and arccosine's derivatives only differ by sign, it's not necessary to have a third integration rule because it's just a constant. So, here's our quick warm-up exercise. I hope you remember from last day that the derivative of arcsine is 1 over the, you guessed it, square root of 1 minus x over 2 all squared. But remember, this is a function, so therefore we have a hook-on factor of an extra 1/2. So we can rewrite this as 1/2 with the square root of 1 minus, and if I were to expand this out, this would be x squared over 4. And what I could also do then is just simplify this a little bit more if I wanted to, because that 2 I can bring inside the square root, and that will become 1 with the square root of 4 times 1 minus x squared over 4, and that just gives us 1 over square root of 4 minus x squared. Okay, so that's our warm-up. Well, here's example number 1. It seems to be exactly the same question, the integration of 1 over the square root of 4 minus x squared dx. Now, let me show you first of all using these rules. If you can see and make the connection, how in this case my a value would be equal to 2, right? A squared 4. And then notice my u value here would be equal to x, since u squared and x squared looks the same. And then just to double check, I should go u prime. U prime of x is just 1. That definitely equals to the top. So if these things satisfy, then guess what? I can just use the formula from above and say, oh yeah, the answer to this is just arcsine of u, which is x over a, which is 2 plus c. Done. Now, if you didn't like that, because you're like, I don't understand where it came from, well, let me show you how I can figure out the antiderivative. So just like how above, where I had this, and now I'm trying to go backwards, notice that I had to pull out a factor of 4. So, without the formula, okay, without formula, our goal is to try and factor out the 4 so I get that 1 minus part, 1 minus x squared. So watch. Square root of 4, bracket 1 minus x squared. And if I do that, this becomes x squared over 4 dx. Make sense? Just like in the previous example, going backwards, That square root of 1 over 4 then becomes my 1/2 outside. And I'm going to rewrite the square root underneath as 1 minus, and also skip a step and rewrite this as x over 2 all squared dx. Now notice my general one is usually always 1 over the square root of 1 minus x. So in this case, notice I have here x over 2. Now I will use U-substitution. So I'll let u equals to x over 2, which then allows me to find du dx, which is 1/2, which allows me to solve for dx as 2 du. And why is this helpful now? I will make my substitutions, and I'll get 1 over the square root of 1 minus u squared. And instead of dx, I now have 2 du. And notice, the 1/2 and the 2 just divide out. And you're left with the integral of 1 over the square root of 1 minus u squared du, which just equals to arc sine of u. And once again, what is u when I replace everything back in? It's arc sine of u, which was x over 2 plus c. Hey, same answer. So once again, if you like the formula, I can see it, boom, you're done in like 2 lines. Without the formula, you can reverse engineer your derivative process, and that's certainly fine as well. You'll get the same answer. Okay. So for this one here, number 2, I hope you can see how this part here equals to your a squared, so a equals to 5. And this part here is your u squared, so that's 2x. In this case, u prime is 2, and I don't have a 2 in my original equation in the numerator, so I have to put it there. And if I put it there, I have to balance it out by putting a 1/2 outside. And so now what I have is a 1/2, and then using the formula up here, it says I take 1 over a, so that's 1 over 5, arctangent of u, which is 2x over a, which is 5, and then plus c. And so if I simplify this, 1/10 arctangent 2x over 5 plus c is the answer. Now, once again, we can do this without the formula as well. And then the goal here, once again, is to write it as 1 squared. So taking a look back at our original equation, I will ask us to factor out the 25. And so now I'll have 1 plus 4x squared over 25. This allows me to then take out the 1 over 25. And now this is 1 over 1 plus, and write this as a square, 2x over 5 all squared dx. And then once again, I hope you can see some u substitution happening here. Let u equals to 2x over 5. du dx is just 2 over 5. So dx is 5 over 2 du. And then, by plugging in and making the substitutions, I have 1 over 1 plus u squared. And my dx now becomes 5 over 2 du. Notice that my 5 over 2 and 1/25 simplify into, you got it, 1/10. And the antiderivative of 1 over 1 plus u is just arctangent of u. And then don't forget plus c. And our final step, once again, is to just substitute back in the u value of 2x over 5. Hey, look at that. Same answer. Life is good. Okay. So I'll let you try number 3 on your own. Okay, it's very similar to number 2. And then once you've done number 3, I want you to notice how questions 3, 4, and 5 all look very similar, but because this is integration, they actually require 3 different methods of integrating. And that's the hard, tricky part about integration. It's not as simple as differentiation with a few steps. There's multiple things you need to consider, and you need to know the different forms. So anyways, I want to leave this for you now to try. Please try number 3 on your own, and then see if also you can do numbers 4 and number 5 as well. Okay? Go ahead. For number 3, once again, I'll do it with the formula and without. If I do it with the formula, that means a in this case is root 3. U in this case is 2x, and u prime equals 2. Well, in this case, u prime is 2, but the number on top is 8. So I can rewrite this as 2, and I'll put the 4 on the outside. So this becomes 4. And then I can say it is using the formula. Where's the formula? Oh, yeah, 1 over a. So 1 over root 3 arctangent of u 2x over a root 3 plus c. And that's your answer. Okay? With the formula. And once again, you don't need to do both ways. I'm just showing you both ways, okay, guys and gals? So with the formula, I guess I will take out the 8 and also factor out the 3 from the bottom. So I'll get 1 plus 4x squared over 3 dx. Notice that this becomes 8 over 3 with the integral of 1 over 1 plus 2x over root 3 all squared dx. You can now use your U-Substitution. Let u equals to 2x over root 3. So du dx is equal to 2 over root 3. And then, of course, dx is equal to root 3 over 2 du. And making those changes now, you'll get 8 over 3, square root of 1 over 1 plus u, all squared, with a root 3 over 2. And that simplifies. If I take the 8 over 3 times root 3 over 2, that just becomes 4 root 3 over 3, with the integral of 1 over 1 plus u as arctangent of u. And I'm just going to keep one more step here with the u, and I'll plug in 2x over root 3 plus c. Now you might be thinking, hey, this almost looks the same, except I have 4 over root 3 and 4 root 3 over root 3. Well, 4 root 3, if I multiply that by the root 3, gives us just 4 root 3 over 3 anyway, so they are the same. Yay! Woo! Now once again, I showed you examples 1, 2, 3 in two different ways. If you can see it without the formula, by all means do that first. Saves a lot of time. Now number 4 is a little bit different, and I hope you could see that the degree in the denominator, the denominator here is 1 more than the degree in the numerator. And so that's usually a key thing to say, hey, let u equals to 3 plus 4x squared. And doing that will allow you to get 8x, and look at that. That's exactly what I need from the top. Perfect. U-sub is the method of choice for something like this. So, integration of 8x over u times du over 8x. Beautiful. The integration of 1 over u du. We know that from Unit 7, that's natural log of the absolute value of u. And then I can replace the absolute value back with 3 plus 4x squared. In this case, I don't even need the absolute value because I know that's going to be positive. Nice. And then that brings us to 5 and 6. Not so nice. Okay. Notice once again that very similar to 3, 4, and 5. This time the degree of the numerator is equal to the degree of the denominator. And here you have to use something you learned in pre-calculus 12. And that is this whole thing called long division. So this is the key strategy to help us with something like this, when the degree of the numerator is equal to the degree of the denominator. Hopefully you remember how to do this. 4x squared goes into 8x squared 2 times. 2 times 4x squared is 8x squared. 2 times 3 is 6. And then you subtract. leaving us with a negative 6. So in essence, what you and I have done is just rewritten that integral as 2, that's your quotient, plus the remainder, which is negative 6, over the quotient. There we go. And now, to do this, I will ask you to split up the integral. And notice that second integral now has a denominator of 3 plus 4x squared, but a numerator of 6. This is very similar to example number 3. So you can do that yourself if you wish using the formula. And I will just actually anti-differentiate 2, which is 2x. And then over here with that formula, I think what it becomes is that this is a 2. Is that right? A 2, yeah, and this can become a 3. Because once again, a equals to root 3 and u equals to 2x. So u prime has to be 2. Remember all that stuff? So this just becomes 3, 1 over a, 1 over root 3. Arctangent of u, which is 2x over root 3, plus c. Okay. There you have it. And finally, for number 6, this is just totally different, but nonetheless, you might be thinking, hey, that square root of 4 minus x squared looks like a arcsine function. You bet it does. But unfortunately, that numerator makes it a pain. So once again, there's a trick for this one too. Guess what you have to do? Split this up into 2 separate integrals. And when you do that, I hope you can see why this is useful. For the first integral on the left, hello, U-Substitution. Let u equals to 4 minus x squared. Lots of U-sub. Okay, negative 2x. dx equals to du over negative 2x. So this just becomes the square root of, x over the square root of u with a du over negative 2x. Goodbye, goodbye. Negative 1 over 2. The antiderivative of u to the negative 1/2 du. And that just gives us, what, u to the power of 1/2 divided by 1/2, so just negative root u. Which of course equals to negative 4 minus x squared to the power of 1/2. And that's the integral on the left. Now the integral on the right, well, we can simplify that as well by pulling out the 4 and just getting 1 over the square root of 4 minus x squared. And I hope this looks very similar, because this is actually from example number 1. So this is the same thing as plus 4 with the arcsine of x over 2. And so of course we can combine it all together. Excuse me. Plus c. And there is your final answer. Whew. Okay, so yeah, we've done a lot, but I want to do a bit more. So can you take a look at the 9.5 supplement page in the back of your work text? I'd like us to take a look here and do a few more types of questions. Yes, there are more types. So remember the integration of inverse trig functions and their formulas. So this one just becomes arcsine of u over a plus c. This one is 1 over a arctangent of u over a plus c. Now, in the previous questions, you can kind of see that there's a sum of squares or a square root of a difference of squares in the denominator. But sometimes you can't see that, and if you can't see that right away, guess what? You're going to have to manipulate it to see squares. Remember how you create a square? Hint, 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 by completing the square. Remember that good stuff from pre-calculus 11? And you're like, oh no, that's right. We have to learn how to complete this square to make it into this format of either a squared minus u squared underneath the root, or a squared plus u squared in the denominator. So, example number 1. Remember how to make this into a perfect square? I would suggest that we take the x squared and the 4x term. And then I like to leave some space. And I ask myself, what number do I need to plug in here to make this a perfect square? Yep, plus 4. And then don't forget balancing it out, minus 4. First 3 terms here then just become 1 over x plus 2 squared. Yay, that's a square! And 8 minus 4 is 4. That's also a square. Beautiful. And I'm thinking, this looks like an arctan question because u equals to x plus 2, u prime equals to 1, and a equals to 2. So once again, you can just go ahead and use the formula or just solve it the long way. I've done enough of the long way today. So if we just quickly use the formula, 1 over a arctangent of u x plus 2 over a plus c, you're done. Okay? Completing the square with a number that is not, the x squared term that is not a coefficient of 1. A little bit more trickier, but nonetheless still doable. Good old factoring comes to save the day. Remember doing this, friends. Think about what magic number goes into here. It's always half of the coefficient of the middle term. So negative 3 all squared is 9. Be careful you don't subtract off 9 because it's actually 2 times 9, so you have to subtract off 18. I can rewrite this as 2 bracket x minus 3 squared. 26 minus 18 is 8. This is nice because I can factor out a 1/2 now, and that leaves me with just x minus 3 all squared plus 4 dx. And once again, using the formula, I can now go ahead and solve this. 1/2 is there. 1 over, well, I guess I should identify u and all that stuff. U, I think, is x minus 3. U prime is equal to 1. And a equals to, 2. So, 1 over a arctangent of u over a plus c. Okay? 1/4. Alright, last one. Ooh, square root. Ooh, negative x. Ooh, not a problem. Because if I factor out the negative x from the x squared term and the 4x term, you'll see that I can also complete the square here by adding 4. And because it's negative times 4, I have to now also add 4. Right? Negative 4 plus 4. That's how you balance it out. And then in this case, once again, you're trying to make this into a square. 25. And I always like to rewrite it like this with the 25 in front, because this is the square root version. U equals to x plus 2. U prime is 1. That's perfect. A equals to 5. We're ready to do the arc sine of just x plus 2 all over 5 plus c. And that's your answer here. Okay. All right. More stuff. Integrating a fraction where the degree of the numerator is greater or equal to the denominator. I did this as an example before using long division, but I'll do it one more time. Just take the x squared plus 2, divide it into quotient goes in once. X squared plus 2 times 1 is x squared plus 2. Notice I like to line things up. Makes it easier to subtract. X squared minus x squared is 0. Negative 4x minus 0 is negative 4x. 2 minus 2 is 0. So this just becomes the integral of 1 plus negative 4x, which is my remainder, divided by x plus 2. And we can quickly rewrite this as 1 dx minus the integral of 4x over x squared plus 2 dx. And I leave this as an exercise for you to do yourself, because the antiderivative of 1 dx should be straightforward. And the second integral, I'll say, let u equals to x squared plus 2. Alright, I'm not going to do this for you. You should be able to do this yourself. You try, please, and you get the answer of... You think I'm going to really tell you? How about I'll tell you in class? See you then. Oh, by the way, next page. Lots of practice questions on these types with solutions. You should do them.